Hey, you know what's easy? The mean value theorem. We're going to do numbers 7 through 12 and 41 and 42, which is just kind of like a review of some other general concepts. Those two are. I think like what you have to do a mean value theorem problem is really easy, and you can get the moves down, I think. But I think it's important to make sure you don't lose sight of what you're doing. The mean value theorem applies. Can we use the mean value theorem here? Yes, because f is continuous and differentiable. You can just say differentiable because that covers both. You can't be differentiable without being continuous, right? F is differentiable on that interval, right? The technical, I think in the notes I went over with you, like technically it only has to be differentiable on the open interval and continuous on the closed interval. But if it's differentiable on the whole closed interval, then you're good, because you got the endpoints too. Okay, so can we use it? Yes. So if you can use it, what does the mean value theorem say? It says that average slope has to actually equal, the derivative has to equal the average slope at some point in the interval. So that means that f prime of x must equal the average slope, which is rise. So look at the 5 in first. That's 5 squared minus 5 minus, this is just slope. You've heard of it. 9 minus negative 3. So there's my rise over run. And be careful with your signs. And that's equal to 8 over 8, which is equal to uno. So the derivative of this, 2x minus 1, has to equal 1 somewhere. I don't know why I made those ones different. That's kind of weird. So x equals 1. And then if the mean value theorem applies, we have to, there's a guarantee, the mean value theorem guarantees that there is a point, an x value, not just any x value, it's got to be in this interval, where the slope is equal to the average slope. The real slope derivative is equal to the average slope. That's what we're doing. Why does that work? Well, this is some kind of parabola thing, right? Because if it's a smooth curve, then it can't smoothly get from here to here without at some point having that tangent line that's parallel. So that's what we found here. Here's our average slope, 1, and here's my spot at x equals 1, where the slope really is 1. That's how you do it. Let's see, let me just flip to the back of my book, make sure I'm not going to tell you anything that's not true. So we're good there. They have c equals 1 because that often these are framed in terms of like the find the c that the mean value theorem guarantees. So we can do it that way from now on. So what do we have here in number 8? I have x cubed plus x minus 4 on the interval -1 to 2. So mean value theorem says that f prime of c must be equal to the average slope, which is plugging 2 in, that's 8, plus 2 is 10, minus 4 is 6. Plug in -1. -1 cubed is -1, minus 1 is -2, minus 4 is -6, over 2 minus -1. That is 12 over 3. Okay, so what's the derivative of this? F prime of x is equal to 3x squared plus 1. So those two have to be equal to each other. And I'll do that C thing that they do. I'll call this 3C squared plus 1. That's the value that the mean value theorem guarantees. Oh, can we use the mean value theorem? Yes, because this is continuous and differentiable everywhere. So you betcha. Subtract 1, so C squared is equal to 1. So C is equal to plus or minus 1. Now, what does the mean value theorem guarantee? Are both of these answers? No. The mean value theorem guarantees that there is a point internal to this. In other words, not the endpoints. The mean value theorem doesn't say anything about the endpoints. It guarantees a C inside this interval. So the one that the mean value theorem guarantees is C equals 1, not the negative one, even though the negative one's right at the edge of that. That's important. Got to make sure that your answer is inside that interval. Number 9. F of x is equal to x plus 1 to the 1/2 on the interval from 0 to 3. So let's see. I should do it this way. Find the derivative here. It's 1/2 times x plus 1 to the negative 1/2 times the derivative of what's inside is just 1. So let's set up my equation here. The average slope, which is 3 plus 1 is 4 to the 1/2 is 2 minus 0 over 3 minus 0 must be equal to the derivative 1/2 at some point C inside this interval. Can we use the mean value theorem on this? We didn't check that out. Well, what does this function look like? It's a square root function, right? And it only has a limited domain, but the domain starts at -1, right? It's the square root function shifted 1 unit to the left. So from 0 to 3, yeah, we're good there. That's all nice and smooth and everything. So you betcha, mean value theorem applies. 2/3, let's see, if I multiply both sides by 2, I'll get rid of that. And then that's 1 over the square root of C plus 1. So maybe I'll flip both sides over and then square both sides. So if I flip both sides over and square both sides, I get C plus 1 on one side. And then if I flip this over, it will be 3/4 instead of 4/3. So 3/4 squared is 9/16. And then if what did I do wrong? I think I must have done something wrong because, let's see. Oh no, wait. Yes, I did. So I'm hesitating here because when I subtract 1 from that, that's going to give me a negative number, and that's not in the interval here. And this should work. There's no problem here with our mean value theorem. So just trying to check here real quick. This could happen to you, right? What do you do in a situation like this? You try to figure out what you did wrong. That's what you do. So let me check my slope here. So when I plugged in 3 to the 1/2, 4 to the 1/2, that's definitely 2. 3 minus 0, that seems to be good. My derivative, that's good. What did I do wrong? I don't know. Hold on one sec. Let me just check here. Good thing these problems are so easy, right? Well, they are. They are. I mean, sometimes you just try to do math and you fail. Happens to the best of us. And I guess I'm putting myself in the best of us in that company. But you might disagree. Oh, wait a minute. What did I do? No? Let's see. So, yes. Oh, I see what I did. I see what I did. My slope is not right. When you plug 0 in here, you get 1. Sorry. That's 1/3. So then when you flip that over and square it, you're squaring 3/2, not 3/4. So that's 3. So that should be, there we go. You probably had that right the whole time. Maybe you didn't even watch the video for this one because it's even. It's it's odd, rather. And you just got it right. So there we go. Sorry about that. Okay, fixed. Next one. Let's see how we do with this one. My f of x is equal to x minus x to the negative 1 on the interval 3 to 4. That does have continuity issues at 0, but that's not in my interval. So I think we look good for the mean value theorem. We can use it. The derivative would be 1 plus x to the negative 2. And my average slope is, when I plug 3 in here, I get 3 minus 1/3, which is 8/3, minus, oh, I should plug the 4 in first, sorry. When I plug 4 in here, I get 4 minus 1/4, which is 15/4, minus, when I plug 3 in, I still get 8/3, over 4 minus 3, which is 1. That's got to be equal to 1 plus c to the negative 2. Average slope equals the actual slope. So let's see, if I multiply this by 4, that's 60 minus 32, that's 28 twelfths. No, just kidding, that's going to be, I'm not multiplying this by 4, I'm multiplying this by 3. 45 minus 32 is 13 twelfths, I believe. Hope I didn't mess that up. Is equal to 1 plus c to the negative 2. So c to the negative 2 is equal to 1/12. So c is going to be equal to the square root, plus or minus the square root of 12. And the answer that we're looking for is the positive one of those, because that's the one that's in between here. If you want to rationalize that, that's 2 times the square root of 3. That's fine, but you don't have to. That rationalizing, not rationalizing, simplifying radicals is a skill that is not really super important for us anymore. Of course, I guess if it was a multiple choice situation, you need to be able to match this up to another version of that. All right. How about 11? 11, do you know what this, without having to think too hard, you know what that looks like? You know what that is? You should. It's one of the functions that we're supposed to be familiar, or class. It's in a class of function that we're supposed to be familiar with. Pause the video for just a sec if you're not immediately sure what that is, and just kind of stare at that, think about it for a minute. Seriously, pause and think about it. Okay, welcome back. It's the top half of a circle with radius 5. If that was a 1, then it would be the top half of the unit circle. That's an important one to recognize. Comes up, and then goes back down again, in fact. So let's see, what's f prime is equal to 1/2 is 25 minus x squared to the negative 1/2 times the derivative of what's inside. All right, that's a little messy. And then, how about when we plug those things in? Let's see, my actual slope, when I plug the 3 in here, I get 25 minus 9 is 16, and the square root of that is 4, not plus or minus 4. Have that deep conversation some other time. And when I plug negative 5 in, I get 0. and then 3 minus negative 5. So it looks like my slope is 1/2. And then the derivative, let's see if we can write this in a way that's a little bit more friendly, easy for us to see what's going on. So the 2's are going to cancel out. I'm going to get a negative x on the top, and then this is the square root of 25 minus x squared on the bottom because of the negative sign there. Okay, so let's see. If this is 1/2 here, and it is, then I could cross multiply. I could multiply this up here times the 1, and then I could multiply this 2 up here times the x. I could do that. If you're wondering, wait, how did you, that's not a 2. I reduced this. This is 4/8, so that's the same as 1/2. Okay, what now? Well, algebra instincts tell me that I should probably square both sides of this. Now you have to be careful when you go around squaring both sides of an equation, because you can get bogus stuff, right? If you're looking at this and saying, wait a minute, this is a square root, that's definitely positive, and this is negative. Well, this number over here is not negative if x is negative, right? That's just a flip the sign. It's negative 2 times whatever x is. So if x is negative, then we're good. And it looks like certainly x could be negative something or other, right? There, so that seems very plausible. And I guess I should have done my c's here to be consistent with the way we've been doing it. So if I add that over there, I get 5c squared is equal to 25. So c is plus or minus the square root of 5. And here, which one of those is in this interval? They both are, but one of them is an extraneous solution because of the squaring of both sides. So if you look at the positive square root of 5, on the positive side here, when x is positive, these are all negative slopes. So there ain't no way that the actual slope could be equal to this, 1/2. So we're looking at c is equal to negative square root of 5. That is the single one answer that we are looking for. All right. And number 12. That f of x is equal to 1 over x minus 1 on the interval from 2 to 5. So f prime of x is equal to, I'm going to think of this as x minus 1 to the negative 1. So it's negative x minus 1 to the negative 2 times the derivative of what's inside is just 1. So that's it. Okay, my actual slope, plugging the 5 in here, is 1/4 minus plugging the 2 in is 1 over 5 minus 2. And that's got to be equal to the derivative. I'm going to go ahead and write that as negative 1 over c minus 1 squared. And now it's time to do math. So I've got negative 3/4 over 3, which is negative 1/4, is equal to negative 1 over c minus 1 squared. So, well, there's different, you can cross multiply, cancel out the negatives, but negative 1 over this, negative 1 over this, so obviously that has to be equal to that. So 4 equals c minus 1 squared. Square root of both sides, plus or minus. When you take the square root of something, you have to introduce the plus or minus. Well, c minus 1. So it looks like c is going to be equal to 1 plus 2 or 1 minus 2. And that is not in our interval. So we're looking at c equals 3. Is the c guaranteed by the mean value theorem? All right, what's up with these 41 and 42 that I picked for you to do? Let's see. 41, we've got a piecewise function here. 3x squared when x is less than or equal to 1, and ax plus b when x is greater than 1. This is a throwback to kind of problem that we've done before. I think you had one on a quiz or test that was kind of like this, right? Find the values of a and b so that f will be differentiable at x equals 1, at that place where it crosses over. Well, if it's differentiable, it must also be continuous. So for it to be continuous, that means that when you plug 1 into this and 1 into this, you get the same thing. And again, you have to get over the fact that you're plugging 1 into this, even though the equal sign is not there, because the part with the little, it's like a ball and socket joint, or socket, I don't know what that's called, like your shoulder joint, right? There's the ball and it goes into the socket, is that what it's called? So like that, where the equal sign is, has to fit into that where the equal sign is not. So we need to plug 1 into both of those things. And what do we get? We get 3 is equal to a plus b, okay? If we want it also to be differentiable, then the derivative has to be the same at both of those. So that means 6x here, and the derivative of that would be a. And if it is, in fact, going to be differentiable, it doesn't matter where you put that equal sign because it has to be the same at both of those. So I'm just sticking with the same, what they did there. There's no guarantee that that's going to be true, right, if we don't get to tweak those numbers. So when I plug 1 in here, I get 6 is equal to a. So a must be 6, and then b must be negative 3. And that's the end of that game. And then 42. We've got a part A and B. Part A, we've got a piecewise function where f of x is equal to x squared and x squared plus 1 on opposite sides of 0. And we want to show that the derivatives are both approaching the same thing, but that f prime of 0 does not exist. So, okay, well, let's just find those derivatives. Again, it doesn't... So you're looking at this and like, what, don't you get to put the equal sign there? No, because the derivative is only going to exist if it's the same at both of these and if the function is continuous. So this is kind of a trick question. It's potentially kind of trick question. You could do this, find the derivative, and be like, oh, great, plug in 0 there, you get the same thing. It doesn't matter if you get the same thing if the two pieces don't link up with each other, like that. Like they could come in and come out at the same derivative, but if it's not continuous, it is automatic fail for being differentiable. So here, both sides the same, so that's what we wanted to show there, but also that f prime of 0 does not exist because f is not continuous at x equals 0. Why is it not continuous? Because the limit as x approaches 0 from the positive side of f of x, not of f prime, just of the actual function itself, is not equal to the limit as x approaches 0 from the other side of f of x. Right? On this side it's 0, on this side it's 1. That was part A. Part B, another piecewise function, x squared, x cubed. All right, we're going to show that the derivative exists, but that the second derivative does not. Okay, so let's see. Is it continuous? Yes. If you want to get technical, because the limit as x approaches 0 from below is the same as the limit as x approaches 0 from above. Just like what we did there. Okay, so is it differentiable? Let's see, that's 2x and that's 3x squared. And I don't get to put the equal sign anywhere until I confirm that they're the same, and they are. So I could put it there, or I could put it there, because it's the same, it doesn't matter. So is it differentiable? Yes. Because the limit as x approaches 0 from below of f prime of x is equal to the limit as x approaches 0 from above. How about the second derivative? That's going to be 2 here and 6x here. I don't get to put the equal sign in until I confirm that they're the same. So plug 0 in here, well, it's just 2. Plug 0 in here, I get 0. So they're not the same, which means I do not get to put the equal sign in, and because they do not agree. So second derivative does f double prime. There's no like second differentiable. We don't really say that. So f double prime exists? No. And the reason is the same, or we state it in the same way, because the limit as x approaches 0 from below f double prime of x is not equal to the limit as x approaches 0 from above. So all these things. Oh, I just realized something, a little technicality here. So these, the derivative is defined in terms of a limit. So that's how we explain those things. Now going back to here real quick, about the continuity, I said yes because this is true. That's actually not enough for it to be continuous. That has to be true, and the limit, oh, you know what, I can just add it to here as another thing, and that limit is equal to what you actually get when you plug 0 in. So in other words, if you don't put that there, you're not guarding against this. You could have a situation where what's the limit as x approaches 0? It's 0 in this case. What's the limit as x approaches 0 from the other side? It's also 0. So it looks like it's coming into the same spot. But the actual point itself doesn't have to be there if that's all that's true. So this also has to be true. It has to also be equal to what you get when you plug 0 into the function. That prevents that situation, puts the point in the right place. All right. Good little review of continuity and differentiability there.